So we just saw something very profound, and let's try that same thing again, just in a different example. Let's get used to this. So we have a vector field f. It is x squared minus y for the first component, 4z for the second component, x squared for the third component. Let's let S1 be the cone. Z is equal to root x squared plus y squared, with z being less than or equal to 2. Use Stoke's theorem. To find the integral over the line integral over the curve C of f dot dr, where C is equal to the boundary of this surface number 1. And this is counterclockwise from above. Okay, so the orientations need degree in order to use Stoke's theorem. Let's just comment. Let's make the note that we actually did this problem last time. So we did this last time. Look through your notes. In fact, we wrote out double integral over S1 of curl of the vector field f dot ds, and we got 4 pi. I remind you that when we did that work, you should go back and look at your own notes. The work was rather tedious. What I'd like to advocate this time is, instead of doing this directly, we're going to do the following thing. I know this sounds a little strange, but instead, let's compute the double integral over a new surface S sub 2 of curl of same vector function f dot ds arrow. Okay, so we're actually going to come up with our own surface. That's the strange and innovative thing about this. It's challenging, but it will actually help us. The trade-off is going to be nice, instead of doing the problem exactly the same way we did last time. So let's just draw a picture here. X, Y, Z. Surface number 1 that was described in the problem was a cone that looked like this, yeah? So the cone, let's see, I'll try to shade this in. Let's try this maybe this way. I'll just try shading like that. Tried. Okay, so there's this cone. S sub 1 is a cone, and the orientation of the boundary, it's this circle, which will orient this way because the question asked that direction. Okay, so there's the boundary. Now the thing is, if we're thinking about using Stoke's theorem, we need a surface whose boundary is that curve C shown in red. Now, S1 is the surface that's described in the problem. It is a surface whose boundary is C, but there's an easier surface whose boundary is C. Let's draw that. I mean, there's many surfaces whose boundary is C, but let's go with an easy one, right? And that easy one is actually a filled in just circle, a disk. So S2 is just a disk. So sorry, the pictures are not as good, but that red circle just drawn here, oriented counterclockwise when viewed from above, that red circle here is meant to be exactly the same red circle. Okay, so let's just, because I don't think my picture is very good, let me clarify what this is. So this is a circle, a filled in circle. Okay, so a disk of radius 2, centered at the point 0, 0, 2. So here's what we'll do now is say, okay, instead of looking at the original problem, and for that matter, instead of even looking at the line integral, we're just saying, instead of doing the line integral directly, we're going to apply Stoke's theorem again, right? So the point is, we're going to set up basically an integral that looks like this, except over S2 instead of S1. So S2 is parametrized by, well, R is equal to angle bracket U cosine V, comma, U sine V, comma 2. Okay, with D being 0 less than or equal to u less than or equal to 2, and v from 0 to 2 pi. Hey, that's one way to parameterize this disk that's right here. A normal vector, sorry, or rather the orientation, typically a function. Here we just get a real nice situation that the orientation is just the upward arrow. Yeah, so everywhere on this disk, traditionally you can have the orientation tilt in different directions, but here we only need because it's flat, or because this disk is completely horizontal, right? So we don't need the orientation to be complicated or fancy. It won't be, and it can't be. It's just 0, 0, 1. Just as a comment, I just want to recall for comparison, for S1, this surface over here, the orientation needed to take into account the point you're at. And what we had for S1, the orientation, I just remind you what we had last time. It was angle bracket negative cosine of v over root 2, negative sine of v over root 2, comma 1 over root 2. So we had a thing that needed to be more complicated last time. But we've got this R, we have this orientation N for the surface S2, and then RU cross RV, we set up, it should be a 3 by 3 determinant. So IJK cosine V sine V 0, and then when we differentiate R with respect to V, we'll have negative U sine V, we'll have positive U cosine V, and we'll have 0. And this will work out to be 0, comma 0, comma U. So the magnitude of RU cross RV is, well, turns out to be the absolute value of U, but since U is between 0 and 2, this just ends up being just U, plain old U. So then based on this magnitude being U, we can now say that ds is, well, it's supposed to be the magnitude of the cross product times a dA, whether that dA is a du dv or dv du. So in our case, we copy this U right there, and then dA we can write as a du dv, or dv. We'll just go with a du dv. We could have a dv du. We could, if the space required it, we could have done polar, but actually in the parameter domain, that's a rectangle. Yeah, so in the UV plane, we just have a filled-in rectangle. Okay, we're also going to need, so we are computing this, we're also going to need the curl of the vector field we were given, and that will just compute offline here. Yeah, it should be negative 4 comma negative 2x comma 1, and since we are going to be setting up an integral with u and v as variables, we should write the curl of f. We should write this new vector field in terms of u and v. So negative 4 comma negative 2. Now the x that's here gets replaced with u cosine v from our parameterization. U cosine v comma, and then there's a 1. Okay, so then the integral that we're computing, via Stoke's theorem. So we were asked to compute the integral over a curve of f dot dr, but due to Stoke's theorem, we can instead compute the integral over the surface, which surface? S2 over this surface. We already did it over that surface last time, but over the surface S2 of, well, following the formula from Stoke's theorem, curl of f dot n ds. And so now we just need to really plug in some pieces here, right? So leave a little bit of space between these integral signs. Curl of f, it's just right above, huh? Negative 4, negative 2u cosine v, comma 1. That's dotted with, then we need n. That's way back up here, 0, 0, 1. So let's put this here, 0, 0, 1. And then the ds, we had just computed that as well. Over here, it was u du dv, which means we can Since the u is the inner integral, we can take the parameter domain information, put 0 to 2 on the inner integral, and put 0 to 2 pi on the outer integral. This integral is actually really nice to do, so let's compute this. Okay, we're going to have integral 0 to 2 pi, integral 0 to 2. This dot product cleans up real nice, doesn't it? Because 0 times whatever plus 0 times whatever, thanks to this vector here, we, we just have, 1 times 1. That's real nice. So all we're left with is really just u du dv. And if you work out all these details, you'll just get 4 pi. And that's good because last time we had worked out that the integral over this other surface was going to give us 4 pi anyway. Again, just a reminder of what we did last time. And you should go back and look. Right, the last time we did the double integral over the surface S1 of curl of f dot, you can either write ds arrow, or more what it looks like when you actually practically compute is n vector ds. And we had, just to remind you what we had worked out last time that was at least somewhat tedious, was integral 0 to 2 pi, integral 0 to 2 of 4 cosine v over root 2 plus 2u cosine v sine v over root 2 plus 1 over root 2, that quantity closed, times u root 2 du dv. And I'm not saying this integral is impossible, but it's certainly actually a lot more work than the work that's involved in the integral that we did, and you would still get a 4 pi here. And the point is that these, of course, final results match as they should. So the whole thing that's going on here with Stoke's theorem, using it twice, once backwards and then once forwards, or however you want to say it, is going from integrating the curl of a vector field over a surface, instead looking at the line integral over the vector field itself instead of the curl. But instead of even doing that, reusing Stoke's theorem to look at the integral of, again, the curl of the vector field over a new surface. It's just that both surfaces happen to share the same boundary.